NASA's Perseverance rover is currently traversing some of the most dangerous terrain ever attempted by a robotic explorer on Mars. Its target is not random. Mission planners are directing the rover towards specific igneous rock formations located along the rim of Jezero Crater, because these rocks may preserve critical information about early Martian history, including volcanic activity, the collapse of Mars's magnetic field, and the environmental transition that transformed Mars from a potentially habitable world into the cold desert we see today. Igneous rocks form when molten material cools and solidifies. These rocks are scientifically valuable because they act as geological clocks. Unlike sedimentary rocks, which are composed of particles deposited over time, igneous rocks preserve isotopic signatures that can be used for precise radiometric dating. By analyzing these signatures, scientists can determine the age of the rock with high accuracy. This provides a fixed timestamp for major planetary events.
One of the key scientific goals is determining when Mars lost its global magnetic field. Billions of years ago, Mars likely had a molten core generating a magnetic dynamo similar to Earth's. That magnetic field protected the atmosphere from solar wind. Once the magnetic field weakened or disappeared, solar radiation gradually stripped away much of the atmosphere. This led to lower atmospheric pressure, reduced surface temperatures, and the eventual loss of stable liquid water on the surface.
The rocks Perseverance is seeking may contain remnant magnetization. As molten rock cools, iron-bearing minerals can align with the planet's magnetic field. Once solidified, these minerals lock that magnetic orientation into the rock structure. By measuring this magnetic signature in returned samples, scientists may determine whether Mars still had an active dynamo when those rocks formed. This is why the current terrain matters. The rim of Jezero Crater exposes rock layers that were previously buried deep underground. Over billions of years, erosion removed overlying material, revealing ancient igneous outcrops. These exposures provide direct access to material formed during key periods of Martian evolution. Jezero Crater itself is one of the most important exploration sites on Mars. Orbital observations revealed an ancient river delta entering the crater. This indicates that liquid water once flowed into Jezero and deposited sediments over long periods. Clay minerals and carbonates detected from orbit suggest prolonged interaction between rock and water. These minerals are important because they can preserve biosignatures if microbial life ever existed. However, the crater rim provides something different from the delta floor. While the delta preserves evidence of water and sediment transport, the rim preserves deeper geological history. Scientists believe some rim rocks may record volcanic processes, hydrothermal alteration, and crustal evolution from much earlier epochs.
Hydrothermal systems are especially interesting in astrobiology. When heat from magma interacts with water, chemically rich environments form. On Earth, such environments support microbial life even in extreme conditions. If similar hydrothermal systems existed on ancient Mars, they may have created localized habitable zones capable of sustaining microbial ecosystems. Reaching these rocks is extremely difficult. The terrain contains steep slopes, fractured bedrock, loose regolith, and sharp rock fragments. Rover mobility engineers must carefully model wheel traction, tilt angle, and surface stability before each drive. Excessive wheel slip can waste energy and cause loss of position accuracy. Sharp rocks can damage wheels, a concern that became significant during the mission of Curiosity.
Wheel damage is a major engineering concern on Mars. Aluminum rover wheels are lightweight yet strong, but repeated contact with sharp rocks creates punctures and tears. Over time, these accumulate and reduce wheel lifespan. Every route decision balances scientific reward against mechanical risk. Another challenge is drilling. Collecting a sample is not as simple as drilling into a rock. Perseverance must first identify a scientifically valuable target using onboard cameras and spectrometers. Instruments such as Pixel and Sherlock analyze mineral composition and surface chemistry at fine scales.
These instruments help determine whether a rock contains minerals associated with volcanic history, aqueous alteration, or organic chemistry.
Once a target is selected, the rover positions its robotic arm with millimeter-level precision. The drill extracts a cylindrical core sample rather than powdered dust. This core is sealed inside a sterile titanium tube designed to preserve sample integrity for future return to Earth. Drilling on sloped terrain introduces additional complexity. The rover must maintain stability while applying force into the rock. If the surface is loose or the rover shifts during drilling, sample quality may be compromised. Autonomous hazard assessment systems continuously evaluate tilt and contact forces during operation. Contamination control is another critical factor. Since these samples may be analyzed for potential biosignatures, preventing contamination is essential. Tubes are manufactured and handled under strict planetary protection protocols. Engineers aim to ensure any organic compounds detected later can be confidently attributed to Mars rather than Earth.
Perseverance is not only collecting samples for onboard study, it is building the first extraterrestrial sample cache intended for return to Earth. This is part of the broader Mars sample return strategy, one of the most ambitious planetary science programs ever proposed. The reason sample return matters is analytical capability. Instruments aboard rovers are powerful, but limited by mass, energy, and size constraints. Earth-based laboratories offer vastly more advanced analysis. Returned samples can be studied using electron microscopy, isotopic mass spectrometry, synchrotron imaging, and high-resolution organic chemistry tools unavailable on Mars. Such analysis could answer some of the biggest unanswered questions in planetary science. When exactly did Mars become uninhabitable? How long did liquid water persist? Did prebiotic chemistry advance toward life? Was microbial life ever present?
Each sealed sample tube represents more than rock. It is a time capsule containing chemical, mineralogical, and isotopic records from another planet. These records allow scientists to reconstruct ancient environmental conditions with extraordinary precision.